Hello, I welcome you all in this course on steam and gas power systems. Today we will discuss centrifugal compressor characteristics. The working of centrifugal compressor we have already discussed in the previous lecture, and in the previous lecture we considered the radial blades of a centrifugal compressor, right, and we have drawn the velocity diagram for inlet, and the blades are moving in this direction. So, this is U1, this is V1 is equal to Vf1, and this is Vr1, right. And in the radial blades, the air will be leaving blades in the radial direction. This is Vr2 and peripheral velocity at outlet, and this is going to be the absolute velocity at outlet. Okay, and this is beta 1, this is beta 2, and this is alpha 2, and this is alpha 1. Now, in many of the applications, the radial blades are not required, radial impeller blades are not required. The vanes, we can have backward curve vanes and the forward curve vanes. So, if the vanes are curved backward like this, in that case the air will be leaving the vane in this direction, opposite to the direction of flow, right, and then this beta 2 will be less than 90 degree, and after this again U2, and then we will get V2, and this is Vr2. Here V2 is reduced, right. Another arrangement can be that there is a forward vane. When there is a forward vane, in that case air will be leaving the vane in this direction, that is Vr2, right, and this is U2, this U2, and addition of this will give the V2. This is V2. Okay. Now, here the value of beta 2 is greater than 90 degree. Now, the issue is which type of vanes we should go for. So, this is the direction of U2, and relative velocity plus U2 will give the absolute velocity. Now, we have three type of vanes. Now, the issue is for a particular application which type of vane geometry we should go for. Now, if you look at this type of geometry, this is one type of geometry, extreme geometry, and this is another type of extreme geometry. Now, in backward vanes and the forward vanes, if you look at the forward vanes, the absolute velocity which is leaving the compressor is very high, or impeller is very high. Here in this case, the absolute velocity which is leaving the impeller is low, and it means in forward curve vane, if all the other parameters are same, RPM and shape is same, pressure rise will be more, because it has important more kinetic energy, because change in peripheral velocity is going to be the same, right, and change in relative velocity may vary, but the outlet absolute velocity is very high. So, pressure rise will if other parameters are remaining same, the pressure rise is quite high in case of forward curved vane. But in forward curve vane, when the impeller is moving in this direction, this side will have high pressure, this side will have low pressure, slip will take place. Further, this is a convex surface. So, definitely the separation will be more, losses will be more. So, forward type of vane is not very efficient type of arrangement. efficiency of backward curve vane is more in comparison to the forward curve vane. But if you want to have high pressure rise, then we should go for forward curve vane, right. So, these are the velocity diagrams for forward and backward and radial flow vanes. For pre-whirl, when in previous lecture also I explained, pre-whirl is provided just to avoid exceeding the sonic velocity inside the compressor, because compressor is rotating with a very high speed, rotational speed 40,000, 50,000 RPM. So, Mach number M is going to be VR1 over gamma RT1. So, we should check from this formula whether inside the impeller the velocity of air is not exceeding the Mach 1. Now, there are other dimensionless parameters to judge the performance of a compressor. These dimensionless parameters are: number one, flow coefficient. Now, flow coefficient denoted by phi is the actual mass flow rate and mass flow rate corresponding to the impeller tip velocity. The mass flow rate corresponding to impeller tip velocity will be, this is the cross section area, velocity and density. This is volume, representing the volume, and this is multiplied by the density, it will give the mass flow rate. So, this is the value of flow coefficient for a centrifugal compressor. The optimum value, normally the optimum value of flow coefficient is 0.3. It varies between 0.28 to 0.32. Second one is head coefficient. Now, head coefficient is denoted by lambda, and it is delta H in a stage divided by kinetic energy corresponding to the blade tip velocity, that is half u2 square. Now, these parameters are used for judging the performance of a centrifugal compressor or comparing the performance of two different centrifugal compressors. Now, third one is pressure coefficient. That is isentropic enthalpy change divided by tip velocity. So, if there is an ideal process, then head coefficient and pressure coefficient are going to be same. Now, the third one, and which is very important, is reaction or degree of reaction. So, reaction or degree of reaction is denoted by R, or in some of the author they denote it by omega also, right. And this reaction is delta H in rotor divided by delta H in stage. Now, change in enthalpy is always Cp delta T in case of gas turbines, this centrifugal compressors. So, it is delta T rotor divided by delta T stage. Okay. And it is equal to 1 minus delta T stator or vanes. Rotor means which is the part of the compressor which is doing the rotational motion, and the stator means the part of the compressor which is static, right, and divided by delta T at stage. Now, delta T is stator, or this is, let us take energy Cp. Cp delta T stage. So, Cp delta T stator. If you remember that in vaneless part and the vane diffuser, the enthalpy change was due to change in kinetic energy. So, it is going to be equal to 1 minus V2 square minus V1 square divided by Cp delta T into the stage, right. Now, again this is equal to, this R is equal to 1 minus Vf2 square, V2 square is Vf2 square plus Vw2 square. Under any case, will component and flow component, their square will give V2 square minus Vf1 square divided by Cp delta T stage. Now, why I have done this in a suppose there is a compressor for gas turbine, this is Vf and this is U1 and beta 1. Vf, V1, this U. Okay. So, Vf1 is V1. At the outlet, this is Vr2, U2, V2, right? And this V2 is equal to Vf2 square, or Vr2 is equal to Vf2, Vf2 square plus Vw2 square. Now, velocity of flow remains constant in this type of arrangement. So, this can be cancelled out and R is equal to 1 minus Vw2 square divided by Cp delta Ts. Sorry, we have to take kinetic energy. So, this has to be divided by 2. Actually, this R is 1 minus V2 square minus V1 square divided by 2 Cp delta Ts. So, this 2 was missing in earlier expression. So, we can make a correction. So, this is going to be 1 minus 2 Cp delta Ts, right, because this R is 1 minus V2 square minus V1 square divided by Cp delta Ts divided by 2. This is energy. So, this 2 was missing in earlier expression. So, I have added it here and now this work can further be replaced as 1 minus Vw2 square divided by 2 Vw2 U2. Now, this Vw2 will be cancelled with this one. So, R is equal to 1 minus Vw2 divided by 2 U2 and only in the case when Vf1 is equal to Vf2. Now, after this we will solve some of the numerical based on centrifugal compressor. The first one is a centrifugal compressor used as a supercharger for aero engine handles 3 kg per second of air. So, the centrifugal compressor is handling air at the rate of 3 kg per second. The suction pressure and temperature are 100 kilopascal and 280 Kelvin. So, suction pressure and temperature. So, P1 is equal to 100 kilopascal and T1 is equal to 280 Kelvin. The suction velocity is 90 meters per second. So, this suction velocity is 90 meters per second. After isentropic compression, the impeller and in the impeller the conditions are 150 kilopascal. So, P2 is 150 kilopascal and temperature is 335 Kelvin and velocity is 230 meters per second. Calculate isentropic efficiency, right? So, work done is in the centrifugal compressor is Cp T2 dash minus T1 plus V2 square minus V1 square by 2. And because this is always in kilojoules, so we should initially we should divide it by 1000 to convert the expression in kilojoules. So, work done is 1.005, this T2 is T2 dash, 335 minus T1 280 plus V2 is 230 and this is V1 230 square minus 90 square divided by 2 into 1000. And this gives 81.7 kilojoules per kg. So, work is 81.7 kilojoules per kg and we have to find isentropic efficiency. Now, T2 is T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 over gamma, right. Gamma is 1.4, so we can take this as 0.286 or so let us take 1.4 here. So, T2 is T1 is 280, P2 is 150 and P1 is 100. So, it is 1.5 raised to power 1.4 minus 1 divided by 1.4. Okay, and this gives the value of T2 as 314.4 Kelvin. Now, we have the value of T2, we have value of T2 dash. Now, isentropic work. This is the actual work we have calculated. Now, the isentropic work, because in rotodynamic machines kinetic energy cannot be neglected, I told you earlier. So, work done isentropic is going to be Cp T2 minus T1 plus V2 square minus V1 square by 2 into 1000 is equal to 1.005 and T2 is we have calculated 314.4 minus T1 280 plus again V2 square, that is that expression is same 90 square by 2 into 1000 and then we get isentropic work as 56.97 kilojoules per kg, right. Then we have to calculate the isentropic efficiency is equal to 56.97 divided by 81.7 multiplied by 100 will give 69.7%. Okay, so that is the difference between a isentropic efficiency of in a gas turbine, what we calculate in gas turbine, right. There we do not consider this kinetic energy, but in actually when in a compressor, when there is a change in the absolute velocity, so this kinetic energy has to be considered while calculating the isentropic efficiency. Now, total work, total power is work done is 81.7. The total power is going to be this multiplied by mass flow rate, that is 3. So, power is 3 into 81.7. So, power is going to be 245.1 kilowatt. Now, overall efficiency of the unit, after the impeller, the air goes to the diffuser, right. When air goes to the diffuser, then Cp T3 dash minus T2 dash, that is from impeller, sorry, the impeller tip to the diffuser. Now, this is between impeller tip to the diffuser, and this is equal to C2 square minus C1 square divided by 2 into 1000, right, and that is equal to 230 square minus 90 square divided by 2 into 1000. Now, we have taken part. Now, earlier while calculating work consumed, we included this also, but now we are exclusively dealing with this, and this will give us the temperature T3 dash, because rest of the things are known to us. So, temperature T3 dash is going to be equal to 357.3 Kelvin. So, if we look at enthalpy entropy diagram, so this is the enthalpy increase from 1 to 2, and this is 2 to 3. Enthalpy increase 2 to 3, 3 dash. This is 2 dash, this is 3 dash. Okay. Now, once we have the T3 dash, now the P3 is P2 T3 dash divided by T2, and this is, we are not considering any loss during this, because it is not given in the numerical value. So, we are considering this as an isentropic process. So, here that case we can take 1.4 divided by 1.4 minus 1, that is gamma over gamma minus 1 or 3.5, whatever value you want to take. And this provides us the pressure P3, that is 188 kilopascal. Right. Now, we have the value of P3 and we have the value of P1 also. Right. Now, with the help of these two values, we can calculate the value of T3. T3 by T1 is equal to P3 by P1 raised to power gamma minus 1 over gamma. Now, considering this, we get the value of T3 as 335.4 Kelvin. Now, we have the value of T3 dash, we have the value of T3 also. So, overall efficiency of the compressing machine is going to be T3 minus T1 divided by T3 dash minus T1. Now, we have all the values, we have value of T3 dash, we have value of T3, we have value of T1 also, and this gives the overall efficiency as 71.6%. Right. Now, we will take up another numerical. This is about a centrifugal blower, which compresses 5 meter cube per second of air from 100 kilopascal and 15 degree centigrade to 150 kilo. It is a blower. The working principle of blower is same as the working principle of centrifugal compressor, only pressure ratio is different. In blower, the pressure ratio is very low in comparison to the compressor. So, the compressor compresses 5 meter cube of air. So, V is equal to 5 meter cube per second from 100 kilopascal and 15 degree centigrade to 150 kilopascal. So, P1 is equal to 100 kilopascal, T1 is equal to 288, 15 degree centigrade, 288 Kelvin, P2 is equal to 150 kilopascal. The flow velocity at inlet and outlet of the machine is the same and equal to 70 meters per second. The inlet and outlet impeller diameter are 0.3 and 0.6 respectively. So, di is equal to 0.3 meter, do is equal to 0.6 meters. The blower rotates 7000 RPM. So, N is equal to 7000 RPM. Calculate impeller inlet and outlet blade angles. So, first of all, we will calculate T2, temperature at the exit. It is going to be T1 P2 by P1 raised to power gamma minus 1 over gamma, and that is going to be equal to, I will write the expression here, T2 is equal to 329.7 Kelvin. Because we have the value of T1, we can take from here. P2 by P1 is 1.5, gamma is equal to 1.4, and from here we will get the value of T2 as this. Now, U1 peripheral velocity at inlet, U1 is equal to pi d1 n by 60. We have the value of n, we have the value of di or d1. So, U1 can be calculated as 109.95 meters per second. Since the diameter has doubled from 0.3 meter to 0.6 meter, so U2 will also be doubled as 219.9 meters per second, right. Now, Cp work is Cp T2 minus T1 specific work is equal to Cw2 U2 by 1000, right. Now, here we have the value of T2, we have the value of T1, we have the value of U2 also. This will give us the value of Cw2, and that is equal to 190.4 meters per second. Sorry, yes, 4 meters per second. It is will component, right. So, by comparing simply Cp T2 minus T1 with the input to the blower, we have calculated the Cw2. Now, once we have Cw2 with us, now we want to calculate blade inlet angle. Blade inlet angle Vf1, U1, Vr1, and this is beta 1. So, 10 beta 1 is equal to Vf1 by U1. Vf1 is 70. So, it is 70 divided by 109.95. From here we will get the value of beta 1 as 32.4 degree, right. Now, similarly we will calculate, so beta 2 is, this is beta 2, this is beta 2, right, and this beta 2 is 10, beta 2 is Vf2 by U2 minus Vw2. This is V1 and this is Vw2 and this is Vf2. So, Vf2 divided by this part, and we have all the values with us, and from here we will get the value of beta 2 as 67.1 degree. Alpha 2 is this one. Similarly, alpha 2 can also be calculated as 10 alpha 2 is equal to Vf2 divided by Vw2, right, and then alpha 2 is equal to 20.2 degree. Now, the third part is breadth of the blade at inlet and outlet. So, we have to find the value of B, and in order to find the value of B, V1 is equal to pi D1 B1 Vf1. This is area, velocity, volume. V1 and is 5 is equal to pi is known to us, D1 is 0.3 into B1 and Vf is how much, 70. This will give the value of B1. Now, the B1 is 7.58 centimeters. Now, similarly V2 for pi D2 B2 Vf2. Vf1 is equal to Vf2, but we don't have the value of V2. Right? We will use the relation P1 V1 T1 is equal to P2 V2 T2. P1 and P2, T1 and T2 are known to us. V1 is with us, we will calculate the value of V2, and this V2 is equal to 3.82 meter cube per second, and this value 3.82 will put here. D2 is with us, Vf2 is with us, which is 70 meters per second, and that will give the value of B2, that is 2.19 centimeter. That is all for today. From the next class, we will start with the axial flow compressors. Thank you very much.